The question is, could you define normal and shear strains? In answering this question, let's start with something that we are familiar with. Remember systems like this where the particles are supported by cables? In statics, we learned to calculate the forces in the cables, right? Which are also the tensions in the cables, right? In the earlier topic of this course, we took it one step further and learned to calculate the stresses, right? If you recall, the stresses in this case are the normal stresses, right? Because the tensions are normal to the cross-sectional areas of the cable, and therefore the corresponding stresses are normal stresses. So there is another side to analysis, which concerns the calculation of deformation and strains. In this example, the cable system will deform like shown in this picture. The picture drawn in blue is what we call the original configuration, and the picture drawn in red is what we call the deformed configuration. In other words, the weight W is going to pull the cables, and eventually the cables will deform into what is shown by the red picture here. So we make the key observation here that the length of each cable has changed. In the earlier topic, we took the forces in the cables and defined what we call stresses, which are forces per unit areas, right? So here what we're going to do is we're going to take the displacement of each cable and define what is called a strain. A strain is the displacement per unit length. Just as sigma is a fairly common notation for normal stress, epsilon here is a fairly common notation for normal strain. And of course I'm implying that epsilon defined here is the normal strain. So let's go ahead and formally define what a normal strain is. Supposing, say, I have a one-dimensional rod or a cable that is subjected to an axial tension P, like shown in this picture right here. This rod has an initial length of L0 and a cross-sectional area A. A tension like P is going to increase the length of the rod. So the length after the application of the tension P is capital L. L minus L0 is called the displacement, which is basically the change in length of the rod, right? Little delta is a fairly common notation for that. Now we define the quantity epsilon as the change in length divided by the initial length. So it will be L minus L0 over L0 or delta over L0. Epsilon is called the normal strain. And you can see epsilon, the normal strain, goes with the change in length. Later when we define shear strains, you will see shear strains goes with change in angles, but normal strain goes with change in length. So this is analogous to the definition of the normal stress. Remember, normal stress equal P over A, right? The normal force that is perpendicular to the cross-sectional area divided by the cross-sectional area itself is called the normal stress, right? So this is very similar to that. A note that I want to make here is that in this particular example, the stress sigma and the strain epsilon are also called the uniaxial stress and uniaxial strain respectively. This is because the geometry and the loading are one-dimensional. The loading takes place along the axis of the rod. A second note that I want to make here is that strain could vary from point to point. So what do I mean by that? Well, let's go back to this example right here, right? We just define one quantity called epsilon as delta over L0. So it's implied that the strain at every point along the rod is considered to be a constant, right? In general, that may not be true because maybe you have a loading that varies along the length of the rod, or maybe your cross-sectional area varies, or maybe your properties vary, right? So all of these will lead to a strain that varies from point to point. So what do we do in that case? Well, we don't have a choice but to resort to the calculus definition of the normal strain. This is the calculus definition of the normal strain, epsilon. Epsilon equal du over dx. This picture illustrates the physical meaning of these two quantities, dx and du. We take the x-axis to be along the axis of the rod. Just as we considered a rod with the initial length L0, Here we consider a small differential length dx. Say this little differential element has increase in length to dx plus du due to loading. The change in length is du, initial length is dx, and therefore the strain is change in length divided by the initial length, du over dx. But the major difference between this and this is here the strain is constant along the length of the rod. Here u, the displacement, could be a function of x, and therefore epsilon, the strain, could also vary from point to point. Another important note that I want to make here is there are two definitions of strains. The first one is called the engineering strain, and the second one is called the true strain. In the engineering strain definition, we use the original length in the denominator, whereas in the true strain definition, we use the current length. Say you're testing a little specimen in the lab, right? As you increase the load from 0, the length of the specimen will change from its original length to something else, right? And that current length will keep on changing as you keep increasing the load, right? So if you use the current length in the definition of the strain, this is called the true strain. But in most cases, even the maximum displacement is very small compared to the original length of the specimen. So in that case, it doesn't matter which definition you use to calculate the strain, you'll end up with almost the same values. And of course, if you have a highly deformable material like rubber or something, then the displacement can be very large compared to the original length of the specimen, and then the two definitions will lead to completely different results. But in this course, to keep things simple, we will use the definition of the engineering strain. Now let's talk about the units of normal strain. Normal strain epsilon is displacement over length. Since each of the two quantities we have here, the displacement and the length, have the same dimensions, right? And therefore, strain does not have a dimension. In other words, strain is a dimensionless quantity. There are always exceptions to most things, right? Here I listed two common practices when it comes to expressing strains. Say we have a situation where the displacement is very small. Say we had a rod of initial length 1 meters, but the displacement is only 480 times 10 to the minus 6 meters, or 480 micrometers. The strain would be the displacement delta divided by the original length L naught. That will be 480 times 10 to the minus 6 meter divided by 1 meter, right? You can see the meter and meter cancel out, and therefore epsilon is calculated to be unitless or dimensionless, right? So is the proper way to define a strain. But in this particular case, since the strain is so small, it's fairly common to write this as 480 micrometer per meter, or simply 480 mu. Mu here stands for micros. So in other words, you would say epsilon is 480 micros. Secondly, it's also very common to express strains as percentage. Like for example, epsilon equals 0.04 would be commonly referred to as a 4% strain. You simply multiply this quantity by 100. Now let's go back to the cable system we considered earlier and see if we can define the strain for one of the cable. Now here I'm going to choose cable BC. Say the initial length of cable BC is L naught, so that'll be this length right there, right? And then the final length is L, that'll be B to C prime, okay? The axial displacement of BC would then be L minus L naught, and the strain in the cable BC would be delta over L naught, where delta is L minus L naught. So this is the normal strain in cable BC, and similarly you can calculate the normal strain in cable AC and cable from C to W. Now let's talk about the definition of shear strain. Say I have a rectangular body CDEF like shown in this picture. Now in that body, I'm going to take two lines OA and OB that are perpendicular to each other and see how they deform. And in the first case over here, I'm applying a shear force V at the top. Supposing, say, this body CDEF deforms like a deck of cards like shown here. The angle between these two lines OA and OB will decrease. Let's say the current angle is theta. The third case shown here is similar to the second case except for the fact that we are applying the shear force in the opposite direction. Now this is going to lead to an increase in the angle between OA and OB. The shear strain gamma is defined as the change in angle between lines that are perpendicular to each other, expressed in radians, and therefore they have no dimensions. Gamma is a fairly common notation for shear strain. In a quantitative manner, gamma in the above cases would be pi over 2 minus theta, right? And you can see it is a positive quantity in case 1 and a negative quantity in case 2. In other words, what we are saying here is if the angle decreases, it's positive. If the angle increases, it's negative. In the example I considered in the earlier slide, I considered a special case where the horizontal lines remain horizontal lines, right? In general, that may not be true. A horizontal line OA could deform into OA prime, whereas the vertical line OB could deform into OB prime. The definition of the shear strain remains the same, change in the angle, right? So that will be pi over 2 minus theta, which in this case would be gamma 1 plus gamma 2. There are two definitions of shear strain. The first one, called the engineering shear strain, is the one that we've been talking about so far. Engineering shear strain is typically denoted by gamma, and it's basically the total change in the angle. There's another one called tensorial shear strain, which I will not elaborate in this video. We'll talk about it later when we discuss three-dimensional nature of strains. Tensorial shear strains are half the value of the engineering shear strain. Like for example, if I take two axes, axis 1 and 2, the tensorial shear strain epsilon 1, 2 between the two is gamma 1, 2 divided by 2. Geometrically, this angle right here is epsilon 1, 2. This angle is epsilon 2, 1, but it can be shown to be equal to epsilon 1, 2, and therefore gamma 1, 2 is 2 times epsilon 1, 2. Anyway, we'll pick up on this later. So far, we've considered two lines, one of which was kind of aligned with the positive x-axis, the other one was aligned with the positive y-axis, right? But in many cases, that may not be true. So we need to have a sign convention to decide on the sign of the shear strain. While there is a basis for this, I will skip that for now and give you the final results for now. In general, there could be 4 different situations. In situation number 1, this axis is in the direction of the positive x-axis. This axis is in the direction of the positive y-axis. In situation number 2, this is in the negative x direction, this is in the negative y direction. Where here, this is in the positive x direction, this is in the negative y direction. In situation number 4, this is in the negative x direction, this is in the positive y direction. It turns out in the first two situations, which I will call case 1, if the total angle decreases like shown in these pictures, right, then the shear strain is positive. In other words, theta here, which is the final angle, is smaller than the initial angle, which is pi over 2, right? So this is true in both of these cases, and then shear strain is positive. In the last two situations, the opposite is true. If the angle between the two lines increases, then the shear strain is positive. In other words, theta here is bigger than the initial angle, which is pi over 2, right? And that is true for both of these cases. And if that is the case, the shear strain is positive. Here's a little example to illustrate the use of the sign convention we just talked about. Here's the summary of the 4 different situations. Here's an example. We have a two-dimensional rectangular body ABCD, and that rectangular body deforms into what is indicated by the red lines here. So there are 4 corners, A, B, C, and D, right? Each of those 4 corners undergoes change in angle, right? The corners A and C are like situations 1 and 2, right? For the shear strain to be positive, the angle must decrease. We do have a decrease in angle at this corner, and therefore the shear strain there is positive, whereas here the angle is increasing, and therefore the shear strain must be negative. The corners B and D are similar to situation 3 and 4, And here, of course, the angles must increase for the shear strains to be positive. We do have an increase in angle at point D, and therefore the shear strain is positive there. Whereas here, angle is decreasing, and therefore the shear strain must be negative.